Hi everyone, this video is a continuation of your lesson in vapor power cycle where we have the Rankine cycle used in your steam power plant. So in this video, I'm going to show you how to solve the simple problem first, which is simple ideal Rankine cycle. So let's read the example of problem that we have here from your textbook. Right, a steam power plant operates on a simple ideal Rankine cycle between two pressure limits 3 megapascal and 50, and also it gives you the temperature of steam at the turbine inlet is 300 degrees C, and the mass flow rate of steam through the cycle is 35 kilogram per second. You need to show the cycle on the TS diagram with all respect to saturation line, and afterward to determine the thermal efficiency of the cycle, also the net power output of the power plant. So let us sketch first the TS diagram with respect to the equipment and all the saturation line. So you were given two pressure, one is 3 megapascal, another one is 50 kilopascal, and in between that 3 megapascal and 50 kilopascal, it gives you at state 3 inlet to your turbine from 3 to 4 here. The inlet temperature to your turbine is equal to 300 degrees C. So let's draw the line first. So that will be your temperature at 3. Next, it gives you your m dot, which is equal to 35 kilogram per second. Now, the question is asking you to find the thermal efficiency of the cycle, which is from your notes. In order for you to find the thermal efficiency of your Rankine cycle, so you make use of your work net, which is the desired output over the required input in order to obtain your thermal cycle efficiency. So when you expand this work net, this is actually the work of your turbine, which is in between 3 and 4. You minus with the work of your pump, which is in between 2 and 1. And it is equal, and you divide it with the desired input, which is in your boiler, happening in your boiler in between 3 and 2. And you were also asked to find the net power output of the power plant. So basically this is actually your work net, but it must be in power, so the unit is in kilojoule per second. So in solving for your thermal efficiency, you will obviously need all your enthalpy value over here. So how are you going to find your enthalpy value? This is the working fluid that you're using steam. So you are going to read all the value at state 1, 2, 3, and 4, which is your enthalpy from the property table. And bear in mind that you have property table for your water. You have TA4, TA5, and TA6. So we will figure out what is the state, what is the phase of each states, so that you can solve this problem. So the aim right now is to obtain all the enthalpy value for each state 1, 2, 3, and 4. So let's start with the first state that we have here, which is your state 1. Or you can start at whichever state that you want, either 2, 3, or 4. As long as the information given to you allow you to read your property table. In this case, in order for you to read your property table, you will need to know two known value first. Okay. For example, you may start with state 3 because you know two known value here, which is your pressure and also your temperature. which the rules of thumb of your to read your property table, if given to you pressure and temperature, so you will straight away read from your superheated table, which is in table A6. So in this case, you are trying to look for your H3, which is H3 is equal to, so you have your property table over here, which is your table X6, and we are looking for your enthalpy value at 3 megapascal and the temperature is 300 degrees C. So take out your ruler. In order for you to find this one, you need your ruler. Right, so place your ruler 300 degrees C, so you are looking for your H. Okay. The first column is for your specific volume, and the second column is the third column is actually for your enthalpy, and the final column is for your entropy. Whereas the second column here is actually for your internal energy. Because this problem is actually an open system, so you straight away make use of your enthalpy over here. So from the table just now, your H3 value is equal to 2994.3 kilojoule per kg. There's another value that you will need later on, which is your entropy value at state 3, which is S3 from your table is equal to 6.5412 kilojoule per kg dot Kelvin. I will explain the purpose of this entropy value later on. So we have done with your state 3. Now we wanted to find out the next state, right? So from state 3 we move to state 4. What is known from your state 4? It is your pressure. P4 is equal to 50 kilopascal because the pressure line along this line is equal to 50 kilopascal. This is actually the condenser, inlet to your condenser, outlet to your condenser. And because the problem is a simple ideal Rankine cycle, right? So this is actually an ideal process. So your entropy value is the same at the inlet and the outlet through your turbine. Remember, outlet from your turbine is actually the inlet to your condenser. So S4 is equal to S3, which is equal to 6.5412 kilojoule per kg dot Kelvin. So the objective is to find your H4. Now at this stage, we are assuming that the state 4 now is in the phase of mixture, right? However, we still need to check with your property table, is it true that the state 4 is in a mixture? Then only you will allow to make use of this general equation, which is y is equal to yf plus x yfg, in order to find out what is H4. And before you can do that, you will need your x4 first. So let's try out this one by one. Alright, so your state 4 is actually given to you the pressure, right? So when it gives you the pressure and another property, in this case you assume that your enthalpy should be in a mixture region, right, which is in HFG. So let's take out your ruler and place it on 50 kilopascal. Alright, now we wanted to justify whether your state 4 here is in a mixture region or is it in superheated region, because in the first place we just sketched this assumption, right? So now we wanted to make sure whether your state 4 here is still in a superheated region, or is it already changed into mixture region. So in doing the checking, what you wanted to see is the value of your entropy here. The value of your entropy over here will determine whether your state 4 is in superheated region or is it already changed into a mixture. So from this property table, let's focus to your entropy value. Right, you place your ruler at 50 kilopascal and the entropy. So 50 kilopascal, the entropy reading for your SG is 7.5931, where your S4 is equal to S3 is equal to 6.5412. So look at the value of your S4 is equal to S3 is this value, and that you have your entropy at 50 kilopascal is this value. So it shows that your entropy at this state is less than the saturated line over here, means that your state 4 is already in a mixture, right? Because if you have 8.5 something, then it is larger than your 7.5. So that, in that sense, if it 8.5, so it's already in superheated region. So you will need to read your H4 from table E6, right? But in this case, your entropy at 4 is 6.5412, and when you try to justify your answers with this state at 50 kilopascal, you will see that the saturated vapor is 7.5. So it justify your relations over here that yes, at state 4, this is already in mixture region. Thus, in looking for your H4, you need to make use of this equation over here. So, your equation here, right? So I'm going to show you on how to make use of these equations. So in solving for your H4, you will need your HF plus X4 HFG, where HF and HFG can be obtained from your property table at 50 kilopascal. So you look at the enthalpy value, right? Which is, this will give you your HF, this will give you your HFG. But where are you going to get your X4? So X4 can be obtained from, again, we make use of this general equation over here to find your X4. So X4 can be obtained from your SF, which is, can be obtained from your S4, which is S4 is equal to SF plus with your X4 SFG. And we rearrange these equations. It will give you your X4 is equal to your S4 minus your SF and over your SFG. And where are you going to find all this SF and SFG is again from your 50 kilopascal, because we are talking about state 4 at the moment, right? And where do we get this S4? This S4 is directly from this entropy over here, where at the early stage we assume that this is a simple, since this is a simple ideal Rankine cycle, so your S3 must be equal to your S4. There's no losses. The process is assumed to be reversible. So you plug in all the value needed, SF, SFG, obtained from your property table. So you will get your value of X4 is equal to this one, and substitute this value into your X4 together with value that you get from your property table. So it will give you finally your H4 is equal to this value. So next we proceed to the next one to find for your state 1 and 2. Now we continue to look for your state 1 where given your state 1, pressure at 1 is equal to pressure at 4, which is 50 kilopascal, and that your H1 is actually equal to your HF at 50 kilopascal. Why? This is because this is your pump. Your pump ideally should be can only work with fluid. It shouldn't be any mixture of gas inside your pump. Alright, so ideally your pump need to work on a fluid phase. Alright, so H1 is actually at saturated liquid for 50 kilopascal, and because given to you pressure, so again you will read this directly from your property table, right, which is table A5. Another value that will be used in solving for the next state, which is state 2, is your specific volume at 1, which is again is actually read at the liquid state of 50 kilopascal. Okay, so for both values you can directly obtain from your property table, table E5, at liquid condition. So next step is to find your state 2. For state 2, in looking for your H2, there is another special relation where you have your work pump is equal to specific volume at 1 times with your pressure at 2 minus with pressure at 1. These equations used to find the work pump where you have a specific volume and you times with the pressure difference, because basically the use of pump here is to pump back your water into this boiler. So you are going to have increase in pressure, but the volume of water to be fed back into this system is the same. Thus, this is why we take the same volume from state 1. And work pump, please note that work pump also can be obtained from this equation where you have work pump is equal to your enthalpy at 2 minus with your enthalpy at 1. So when you rearrange both equations, you will see that your H2 can be obtained from this equation up here. So let's rearrange that. Thus, you will get your H2 is equal to specific volume at 1 times with the difference of pressure plus with the enthalpy at 1. So please note that all this value is actually already being obtained previously. So you have your V1, so you plug in over here. P2 is already given here 3 megapascal. Your P1 is 50 kilopascal, and your H1 also obtained from state 1. So we solve this equation and finally we get your H2 is equal to. Now you can see that I'm highlighting the unit over here, right? Because often students get confused with the units. We need to left these answers all homogeneous in kilojoule per kilogram. That's why we change this 3 megapascal into kilos first. So it becomes 3000 kilopascal, right? Then only we can have a homogeneous unit in here. Alright, so we already have all the value needed. So we have your H1 over here, we have your H2 from here, your H3 and your H4. Now it is time to solve for the first question, where you need to find the thermal Rankine cycle efficiency, and then later on you will need to find the work net output power, which is in kilojoule per second. So we plug in all the values that you obtain for your enthalpy, and finally you will get 0.271, or if you change it, you times with the percentage, it will give you 27.1%. And finally we are going to find the power, which is question number 2, asks you to find the power. So it is m dot times with the difference of your turbine work and your pump work, right? And this is the answers in kilowatt, or you can convert it into megawatt. So if you can see from the efficiency that you obtain here, the thermal efficiency for this simple ideal Rankine cycle is very low. It doesn't even reach 50%, right? So in next lesson, we will learn on how to improve this thermal efficiency, so that we will fully utilize the source of heat that we have here. Because as I mentioned before in class, that the source of heat may come from your natural gas, from the biomass, from fossil fuel like petroleum and charcoal, right? So all this will affect the cost in order to get the steam from your boiler here. Okay, so in next video we will see how is your thermal cycle in actual Rankine cycle, and how can we improve it using your reheat Rankine or regenerative Rankine cycle. Thank you.